The lie, time does not exist. Your next second never arrives because physics says it already exists. If that sounds wrong, good. Today I'll give you the three models that make it click. The block universe from relativity, quantum erasers that scramble your idea of before, and entropy's arrow that fakes a flow. The stakes are big: free will, memory, cause, and effect. You'll get a simple test to feel no time, plus a practical way to think in spacetime. There's one mistake that ruins almost every time explanation, and a secret step that makes this 10 times clearer. Stay to the end for a fast visual trick you can use today to think in spacetime like a pro. We start by breaking the flow you feel every day. The flow you feel versus the laws we use. Your experience insists time flows. Seconds tick, moments pass, the past slips behind you. But when you open a physics textbook, the equations don't point to any moving now. They lay out relations between events. You input conditions, you get correlations. Nothing in the math waves a flag saying, this instant is special. That gap, felt flow versus formalism, is where most confusion starts. Relativity's killer move was simple and brutal. There is no universal clock. Different observers, moving at different speeds or sitting in different gravitational fields, don't agree on what events are simultaneous. You and a fast-moving astronaut won't share the same now slice across the universe. That's not a philosophical quirk. It's baked into how spacetime works. When Einstein stitched space and time together, the very idea of a single, global present fell apart. The thing most people miss is this: physics predicts correlations across spacetime, not the motion of a present. In relativity, you calculate how clocks compare when they reunite, how light signals connect events, how world lines intersect. You never need a sweeping pulse that drags reality forward. The math is time-symmetric at its core. If you flip t to t in many fundamental equations, they still hold. So where does the sense of forwardness come from? Hold that. We'll earn it. Let's make the lack of a master clock tangible. Imagine two lightning strikes hitting opposite ends of a moving train. For a person standing on the ground at the midpoint, the flashes can arrive at the same time, simultaneous. For someone sitting at the midpoint inside the moving train, the flash from the front meets them earlier than the flash from the back, because they're moving toward one and away from the other. Same events, different judgments of now. There's no contradiction because simultaneity itself is relative. The flow you feel can't be a feature of the universe as a whole if different observers slice the universe differently. But wait, don't we have memory of the past and predictions of the future? Isn't that proof that time flows? Not really. Memory and prediction are asymmetric data, not evidence of a moving present. Your brain is a recording device that keeps physical records, neural states, photos on your phone, tracks in a cloud chamber. Those records correlate with earlier events. You don't store future records because you haven't interacted with those events yet, not because time is literally flowing. It's an asymmetry in available information, not in the laws. Here's a practical check you use every day: GPS. The satellites are racing around Earth fast enough and high enough in a weaker gravitational field that their clocks don't tick like clocks on the ground. Special relativity says fast clocks tick slow. General relativity says deeper gravity wells make clocks tick slow. In combination, GPS satellite clocks would drift by kilometers per day if we ignored relativity. Engineers pre-correct the satellite clock rates and continuously adjust timing so your phone gets your location. You already live in a world where time is not universal. Navigation works only because we accept that. A student once told me they didn't believe time dilation until they saw the raw GPS drift graphs in a lab exercise. The moment they turned on the relativistic correction module, the position error, meters per minute, collapsed toward zero. They didn't see time slow down. They saw correlations line up when they used the right spacetime model. That's the key. Physics doesn't show you a flowing present. It shows you better and worse ways to relate events. Now here's where most people mess up. They conflate change with flow. Of course we observe change. Atoms vibrate, planets orbit, people age. But describing change doesn't require a moving spotlight of now. It requires an ordering of states and rules that relate them. The equations evolve data along world lines or between hypersurfaces without elevating any instant to a privileged status. Think of a film reel. Every frame exists. The projector's sweep is like your consciousness stitching frames into motion, not a property of the film itself. Once you nail that, everything else clicks. If no universal clock exists, asking what is the universe doing right now becomes ill-posed. Better question, how are events related in spacetime? That shift cleans up countless paradoxes. For example, the twin paradox in special relativity isn't about who had more real time. It's about which world line is longer in proper time. The twin who accelerates, turns around, and reunites has a different spacetime path, so their clock reads less. No flowing present needed, just geometry. The game changer nobody talks about is that many fundamental laws are time reversal symmetric. Maxwell's equations for electromagnetism, the Schrödinger equation in quantum mechanics, and even Newton's laws look fine when you run them backward mathematically. So why do we remember the past and not the future? Why do eggs break but not unbreak? The laws don't pick a direction. Our universe's boundary conditions and statistics do. That's coming soon. But first, we need a solid mental model for what reality looks like when you stop imagining a moving now. Before we continue, you need to understand that our measurements are always about relations. This clock compared to that one, this event's light reaching that detector, this tick count versus that tick count. There's no absolute standalone time reading floating free of observers and fields. Even in particle physics, lifetimes are measured by decay statistics relative to detectors' frames. Every time is anchored to a process, a clock, and clocks are physical systems with world lines. Okay, so what's the quick test to feel no time? Hold your breath and listen for a full minute with your eyes closed. You'll notice your mind keeps trying to count beats to insert markers. The feeling of flow is your brain laying down, updating and comparing records in a rolling window. When you drop the markers, the minute stops feeling like a river and more like a shape. It's crude, but it highlights that your sense of passage depends on internal bookkeeping. Now a complexity warning. Nothing in this says cause and effect vanish. Causality is alive and well, but it doesn't come from a universal ticking. It comes from the structure of spacetime itself, the way signals can and can't travel. We'll pin that down with light cones soon. For now, remember, the laws give relations between events. The flow you feel is a construction on top. If there's no master clock, what does reality look like? It looks like a four-dimensional structure where your now is just one of many possible slices. That's the block universe, and once you see it, the insistence on a flowing present fades. The block universe, all moments exist. If there's no master clock, stop picturing reality as a movie playing and start picturing a finished film reel. In the block universe, spacetime is a four-dimensional structure. Every event, your birth, this sentence, your last message decades from now, exists as a coordinate in that structure. Past and future aren't moving toward or away from you. They're locations along your world line. You don't travel through time. Your world line is the curve that already lives in the block, and your brain experiences local segments of it as now. Why believe this? Because Einstein's relativity breaks the idea of a universal present. Different observers slice spacetime into space and time, differently depending on their motion and gravity. If the present depends on your motion, then it can't be an objective thing the universe obeys. The math is more natural if we treat the whole four-dimensional geometry as real. That's why many physicists and philosophers adopt the block. It matches what the equations actually compute, relations between events across spacetime, not a flowing spotlight. Here's a clean mental model. Think of a loaf of bread as spacetime. Each slice you cut is a now surface, everything you call space at a given moment. Change the angle of your knife and you cut different sets of points. Different observers are just different slicers. There isn't one true slice. The loaf is the thing that exists. Slices are how observers partition it. Your present is a section through the loaf, not a privileged layer the loaf creates on its own. The reason this works is that physics cares about invariant relations, intervals, worldline lengths, light-like connections, not about a moving present. Proper time along a worldline is the spacetime analog of distance along a path. When two clocks reunite, we compare their accumulated proper times. That comparison is geometric. It depends on curvature and motion, not on whether a universal second hand swept over everything. The equations that get predictions right, Lorentz transformations, geodesics field equations, are statements about the block structure. Now here's the thing most people miss. Calling the block fate isn't quite right. The block picture is a description of the full solution to the laws plus boundary conditions. It doesn't add a script. It's the geometry that results from dynamics. If you solve the equations given the universe's initial conditions, the set of events that obey those laws is the block. The block isn't forcing outcomes. It's the record of what outcomes satisfy the constraints. Think map of the entire route you took, not puppet strings pulling you. A quick win to ground this. Draw a space-time diagram with time upward and space horizontal. Sketch your world line as a nearly vertical line at x equals. Sketch a GPS satellite's world line slanted because it's moving relative to you. Now try to draw a line that represents simultaneous for you, horizontal. Do the same for the satellite. Its simultaneity line is tilted because of relative motion. The now that cuts through your event doesn't cut through the same events for the satellite. Both are valid slices through the same four-dimensional structure. That visual kills the idea of one universal present. Now the pushback. If all events exist, how do we account for choice? Doesn't that freeze everything? Hold that thought. In the block, choices are events too, neural configurations, muscle activations, embedded in the geometry. The sense of openness is a perspective from inside the block with incomplete information about later slices. From your local vantage, many futures look possible because you don't have records of those parts of the block. Epistemic uncertainty, not ontological indeterminacy. Whether fundamental indeterminacy exists depends on your quantum interpretation. But the block itself doesn't force fatalism. Another common trap is thinking the block erases causality. It doesn't. Causality is baked into the block by light cones, which events can be connected by signals. You can lay cones at each event. Only events inside your past light cone can influence you, and only inside your future light cone can you influence. Those geometric constraints structure the block's allowed correlations. There's no moving clock needed to enforce before and after locally. Geometry does it. We'll dig into cones next, but keep the link. Block doesn't mean anything goes. This clicked for me when I stopped asking what's happening right now far away and started asking which events are space-like, light-like, or time-like related to me. That shift removes paradoxes like, what if the star blew up right now? For someone moving fast, your right now might cut through a different state of that star. There's no contradiction because simultaneity is a slicing choice, not part of the star. The star's entire world tube, its path through spacetime, exists in the block. Here's the shortcut nobody teaches. Think relations and records. Relations are the invariant geometric connections between events. Records are physical traces, photons reaching your telescope, imprints in detectors, synaptic patterns in your brain that correlate your current slice with earlier slices. When you build knowledge, you're gathering records from your past light cone. In the block picture, knowledge is a structure of correlations, not a moving pointer dragging facts from future to past. Let me give you a micro story that helps. A researcher once framed the twin paradox to me as a hiking problem. Two hikers start and finish at the same cabin. One takes a straight, steep trail, the other takes a winding loop. The lengths of the trails differ. Proper time is trail length in spacetime. The younger twin took the shorter trail. Nobody asks if a present flowed faster on one trail. We just measure the path. Once I saw it that way, the block stopped feeling abstract. Okay, so what does change mean in a block? Change is a relation between different slices. The laws give you constraints that relate fields and particles across the loaf. Evolution equations are just ways to generate the whole block from an initial slice and rules. In practice, We calculate forward because it's useful. But the block view says the full solution is one geometric object, not something being created on the fly. That's why retrodiction, inferring the past from the present, works with the same laws as prediction. There's a complexity warning here. The block universe is a model aligned with relativity. It doesn't dictate your metaphysics about consciousness or free will. You can be a compatibilist about choice and still use the block. Or you can explore quantum interpretations. Everett's many worlds gives a thicker loaf with branching structure. Collapse theories pick a single thread. The block is agnostic about which quantum story wins. It's the classical spacetime stage that all those stories must respect at large scales. If you remember nothing else, remember this. The block universe is not saying time doesn't exist. It's saying the flow doesn't. Time is a dimension in the geometry, measured by proper time along world lines, but not a cosmic conveyor belt. When you think in blocks, you stop looking for a universal present and start reading the map, world lines, cones, and correlations. And once that mental model settles, causality becomes geometry, and the confusing parts of before and after start to clean up fast. Causality without flow, light cones and world lines. Here's the pivot. Causality doesn't need a flowing present. It needs geometry. In relativity, every event, think point in spacetime, comes with two cones, the past light cone and the future light cone. The past cone contains all events that could have sent a light speed or slower signal to reach this event. The future cone contains all events this point can influence with any lawful signal. Everything outside both cones is elsewhere, space-like separated, meaning no influence can travel between them without violating the light speed limit. Why does that settle cause and effect? Because nothing outruns light in relativity. If A sits outside B's past light cone, B cannot have received any lawful influence from A before it happened. Flip it. If B is outside A's future cone, A can't push B. Causality becomes a statement about which events are time-like or light-like related, not about what time is it now. The ordering that matters is invariant. If event A is inside the past cone of B, all observers agree it can affect B if A and B are space-like separated. All observers agree neither can influence the other, even though they may disagree on which one happened first in their coordinates. Let me show you exactly how to visualize this. Draw time vertically, space horizontally. At an event, call it you checking your phone. Draw two diagonal lines at 45 degrees. Those are light rays in flat spacetime. Everything within the downward cone could have reached you. Photons from the screen, signals from satellites, your friend's text routed through towers. Everything within the upward cone is what you can affect next. The phone's pixels, your voice hitting a microphone, a spacecraft you ping with a radio burst. The cones carve spacetime into can touch and can't touch regions. The thing most people miss is simple. Inside the cone equals can affect, outside equals can't. That's the shortcut. It's not fate, it's a constraint. The cone doesn't write a script for what must happen, it fences off what may happen without breaking the speed limit. Within those fences, dynamics and chance, classical chaos or quantum amplitude still do their work. But the fences don't move with a global clock. They're anchored to events and the metric, which tells you how spacetime is curved. Now here's where most people mess up. They think if one observer says event A happens before event B, then A must cause B not if they're space-like separated. Change your state of motion, and the order can flip without changing any physical possibilities. Only time-like or light-like separation gives an invariant before, and after that everyone must respect. That's why paradoxes evaporate when you check separations instead of arguing about simultaneity. Let's put this to work with a concrete example. Take two far-flung neutrino detectors and a supernova burst spraying neutrinos across the galaxy. In one inertial frame, detector east logs arrivals before detector west. In another frame moving relative to Earth, the order can swap for some individual detections because the events are space-like separated. Crucially, no alarm bell rings because neither detection causes the other. Each detection sits outside the other's light cones. All observers still agree on the causal story. Both detections trace back inside their past light cones to the supernova's world tube. Once you nail that, everything else clicks. The twin paradox, the moving train lightning scenarios, even network synchronization and GPS all reduce to geometry. If you remember nothing else here, remember this: causality is local and cone-shaped. You don't need a universal tick to enforce it. You need a metric that caps speeds and defines light-like paths. In curved spacetime, near mass and energy, those cones bend and tip, but the rule stays. No signal escapes outside. Actually, let me back up and make the metric role clearer. The metric tells you the interval between events, how to measure time along world lines and the speed of light locally. In special relativity, cones are perfect 45-degree napkins. In general relativity, curvature warps those angles in coordinates, but locally light still sits on the cone. That's why gravitational lensing works. Light's geodesics curve, yet they remain light-like. Your causal fences flex with curvature, not with a global now. This clicked for me when I stopped thinking of cause as a chain pulled forward by a clock and started thinking of cause as a network of allowed paths. Signals trace world lines inside cones, fields propagate disturbances on or within cones, and interactions happen where world lines intersect. You can even see this in field theory. Retarded solutions, which carry influence from past to future, respect light cones. Advanced solutions, which mathematically run influence from future to past, are usually excluded by boundary conditions that pick the retarded Green's function. The reason this works is that the physics we observe is consistent with influences emanating from past cones. Now the game changer nobody talks about. You can disagree on time order for space-like events and still build consistent, causal stories that match all measurements. That's why Bell test experiments go to great lengths to make measurement choices space-like separated, so no subluminal, hidden signal can carry one setting to the other in time to fake quantum correlations. Regardless of who went first in some frame, the cones forbid ordinary communication between the measurement stations in the relevant interval. Common mistake to avoid: mapping the cones to destiny. The cones don't say what will happen, they say what can, given the speed limit and geometry. Dynamics supply probabilities or determinism. The cones supply the allowable channels. Another mistake: thinking that if cones allow a path, the influence must occur. Possibility is not obligation. The block contains both the fences and the actual path world lines took. Let me give you a quick win you can try. Next time you plan a deep space communication scenario, say, a Mars rover ping, sketch a spacetime diagram. Earth's world line, Mars's world line, and the light-like message lines. Add the rover's processing delay as a small time-like segment, then draw the return signal. You'll immediately see round-trip latency and the windows where commands can arrive before certain maneuvers. No metaphysics, just cones. Before we continue, you need to understand one subtlety. Causality is local, but coordinating complex systems requires stitching many local cones together. That's what mission planners, power grid operators, and even internet protocols do: propagate signals within allowable cones and keep state consistent without assuming a universal present. Once you think this way, retrocausality claims get a lot less spooky because you'll ask the right question: are the strange correlations still confined within everyone's light cones? If yes, the geometry's doing its job. Now, let's confront the quantum experiment that seems to cheat: the delayed choice quantum eraser. Quantum erasers and the past that changes. Now the part that freaks people out. The delayed choice quantum eraser makes it look like the future edits the past. Here's the setup in plain terms. Start with a double-slit source of single photons. If you don't learn which slit a photon goes through, the screen builds an interference pattern, bright and dark fringes, because the quantum amplitude goes through both slits and interferes with itself. If you mark which path, add a tag that lets you tell slit A from slit B, the interference vanishes and you get two broad lumps. So far, standard. The twist is to entangle each photon with a partner and delay the decision to keep or erase which path information about the original after it's already hit the screen. In common versions, the signal photon flies straight to a position-sensitive detector. Its entangled idler is routed through a maze of beam splitters and detectors that either preserve which path info or erase it by mixing paths. Crucially, the idler's detection happens later, sometimes after the signal has been recorded. When you then sort the signal detections into subgroups based on which idler detector clicked, interference reappears in the erased subsets and disappears in the which path subsets. It feels like your later choice decides whether earlier photons interfered. Why this matters is obvious. It hammers our naive first this happened, then that narrative. But the thing most people miss is that there's no message to the past, no change to any recorded past data. If you look at the raw pattern on the main screen without conditioning on idler outcomes, you never see clean interference, just a washed-out distribution. The fringes only snap into place after you pair each signal event with its corresponding idler event and keep the appropriate subset. That conditioning is key. The correlations live across the entire setup as one entangled process. Let me show you exactly how to hold it in your head. Think global pattern instead of step-by-step time. The experiment prepares an entangled two-photon state. That state encodes potential correlations across the whole apparatus, including your later beam splitter choices. When you keep only the signal photons whose idlers hit the eraser detectors, you see interference shifted one way. Keep the complementary eraser port, and you see interference shifted the other way. Add the two subsets back together and the fringes cancel, giving the bland overall pattern you always had. Nothing about the earlier screen image changed. You just relabeled events using later information. Now here's where most people mess up. They say, so we controlled the past. No, you can't use this to send a readable bit backward in time. If your friend controls the eraser choice at the idler station, the signal screen alone never shows a toggle you can read in real time. You only recover the fringe versus no fringe distinction after you compare logs, classically communicate, which lives inside ordinary light cones. The reason this works is that quantum mechanics limits what information is locally accessible. Entanglement gives you correlation stronger than classical, but it doesn't give you backwards messaging. Actually, let me back up and make the statistics crystal. Without conditioning, P screen position is a smooth sum of two interference patterns shifted half a fringe out of phase. That sum is flat. With conditioning, P screen position idler at D1 shows fringes. P screen position idler at D2 shows anti-fringes. You can't see either conditional distribution at the screen alone. You need the idler tag to build the subsets. That's the secret step that makes this 10 times clearer. Always ask, what distribution am I looking at, marginal or conditional? The mental model I like is a deck of cards split into two envelopes by suit. If you only look at the pile of drawn cards, it looks random. Later, when someone tells you which envelope each card came from, patterns appear inside each subgroup. You didn't change the earlier draws. You resorted them by information you gain later. Quantum erasers are that idea with amplitudes and entanglement, not classical suits, but the logic of conditioning is the same. So what does the block universe say here? Treat the entire experiment, source emission, beam splitter paths, detector clicks, your decision switches, as one spacetime story. The correlations are fixed by the quantum state plus the apparatus configuration. In the block view, there's no need to picture a present marching forward and being edited. The full set of events and their relations is the solution. Your later data processing choices select structures already implicit in that solution. The game changer nobody talks about is that retrocausality is often just our poor language for time-symmetric laws plus asymmetric information. Quantum dynamics in many formulations are time-reversal symmetric at the micro level. What picks the retarded direction we experience are boundary conditions, decoherence, and the entropy gradient. In the eraser, decoherence is delayed until you either keep which path markers or erase them by recombining. That delay keeps phase information available to show interference in the sorted subsets. No paradox required. Common mistake to avoid: calling erasure destroying information like shredding a file. In many implementations, erasing means arranging the idler interferometer so that path labels become physically indistinguishable, letting amplitudes reunite. If you let the which path tag leak into the environment, stray photons, thermal vibrations, you've decohered and interference is gone for good. Erasers only work while coherence remains in a controlled subspace. Here's a quick win to cement it. Draw two columns. Left is the signal screen positions. Right is the idler detector index. Now sort the left column by each right column label. Watch two sinusoidal patterns emerge with opposite phase. Compute the unsorted histogram and watch the ripples cancel. Once you do this once with sample data, real or simulated, the future changing the past story loses its grip, and global correlations conditioned on later info becomes the obvious read. This clicked for a student when we tried a simple optics analog. We built a mock Zander interferometer with single photon attenuation and a removable which path marker. With the marker in place, the output intensities balanced, no fringes at the downstream camera. Remove the marker or recombine paths with an extra beam splitter, and fringes appeared, only after we gated the frames by a synchronization pulse that labeled which shots had the recombination. The raw, ungated camera roll looked flat. The gate, our idler log, revealed the pattern. Same lesson, fewer mirrors. Before we continue, you need to understand the philosophical caution. Saying the past changes invites confusion. What changes is your description when you condition on new records. The physical records themselves, screen hits, detector clicks, sit fixed in spacetime. The block plus quantum correlations tell you which records line up with which interference structure. If you remember nothing else, remember this. No messaging to the past, just all-at-once correlations revealed by selective bookkeeping. And with that, we can ask a sharper question. If we can do physics without a moving present, do we need time as a fundamental ingredient at all? Timeless physics, configuration not clocks. If the block universe dissolves the need for a moving present, here's the next leap. Many powerful formulations of physics work without treating time as a fundamental input. The thing most people miss is that evolution in time is often just a convenient way to parameterize changes between configurations. Under the hood, the laws relate whole states to whole states. Clocks are physical systems inside those states, not an external metronome telling the universe what to do. Let me show you exactly how to think about this. Imagine the universe as a stack of configurations, complete snapshots of all fields and particles. A configuration isn't a photograph. It's the full specification of what exists and how it's arranged. Change is the ordering of configurations that satisfy the laws. You can label that ordering with a parameter we call t, but the parameter is bookkeeping, not a master clock. This clicked for me when I realized I could derive dynamics from a principle that doesn't start with time at all, like a path that extremizes an action, or a geometry that makes relational distances fit best. Why do physicists even do this? Because it strips away unnecessary structure and exposes what's physically meaningful: relations, not coordinates. In classical mechanics, the action principle says the actual path between two boundary configurations is the one that extremizes the action. You can specify the start and end states and derive the in-between without invoking an external clock. In general relativity, the Einstein equations can be posed as constraints on allowed 3D spatial configurations, plus relations that connect nearby slices. The Hamiltonian constraint, the famous H equals, is a reminder that the total energy generates no global ticking. Time is what an internal clock measures along a chosen slicing. Now the game changer nobody talks about. In quantum gravity attempts, the problem of time shows up as an equation that looks timeless. The Wheeler-DeWitt equation, schematically h psi, says the wave function of the universe satisfies a constraint, not a time evolution law. You get dynamics by picking an internal degree of freedom to act as a clock relative to which other degrees of freedom change. That's relational time. There's no God parameter t outside the universe. There are only correlations among parts of the universe. Here's a clean mental model. Treat nows as nodes in a graph. Each node is a full configuration. Edges connect nodes that are allowed to neighbor each other by the laws. A history is a path through this graph. You can label nodes with entropy, with the reading of a particular clock subsystem, or with any monotonic feature, but the graph itself exists without a preferred label. The reason this works is that the laws are constraints that carve out which configurations can sit next to which. The label is a convenient index, not a cause. Now here's where most people mess up. They think timeless means frozen. It doesn't. Timeless means the fundamental description is about lawful relations between configurations, and time is an emergent parameter we extract from those relations. You still recover motion, waves, growth, decay, everything, by comparing one configuration to another along allowed sequences. The trick is picking a good clock variable. That's where entropy comes in. Shortcut nobody teaches. Use entropy as a label for sequence, not as time's engine. Entropy tends to increase along macroscopic histories because low entropy boundary conditions make that direction overwhelmingly likely. So you can often order configurations by a coarse-grained entropy measure and treat that as a surrogate arrow. The reason this helps is it decouples two questions we often mash together. What sets the direction of our experience, and what the laws fundamentally require? The laws can be time-symmetric. The sequence you live through follows the entropy gradient. A practical benefit of this view is clarity. It separates psychological flow from physical description. When you simulate a system, you step it forward in discrete ticks because computers need loops. But what you're really doing is constructing successive configurations that satisfy update rules. You can check reversibility, you can retrodict, you can choose different variables as your clock and still get consistent stories. In the lab, when you measure a decay lifetime, your time is the reading of a cesium clock or the oscillations of an optical lattice. Internal processes, not an external timeline. Let me give you a micro-story. In a student project on molecular dynamics, we once lost the global time-step variable by mistake, but we still reconstructed trajectories by pegging positions to the phase of a reference oscillator in the simulation. We used that oscillator as an internal clock and rebuilt velocity distributions and collision sequences perfectly. The physics did care which parameter we labeled time. It cared about consistent relational data across configurations. There's a limitation you need to keep in mind. Timeless formulations must recover ordinary dynamics where we've tested them. You should be able to pick a good internal clock, an atom's oscillation, a gravitational wave phase, the heartbeat of a pulsar, and reproduce familiar evolution equations with the right statistics. If a timeless model can't explain why two clocks agree within uncertainties when they meet, it's not a good model. The test is consistency with records, not elegance. Okay, so how do you apply this mental shift today? Start describing systems by the records they carry and the constraints they obey. In cosmology, think of the early universe's low-entropy boundary as a special configuration that seeds an arrow. In quantum experiments, track how apparatus states correlate and decohere, not when a wave function collapses. In relativity, choose a foliation, your slicing of spacetime, and define time by proper time along a convenient world line. You'll notice that your predictions don't depend on a global tick, only on consistent mapping between configurations. Before we continue, you need to understand one subtle point. Good clocks are limited. Any physical clock interacts, drifts, and ages. Quantum limits like the energy, time uncertainty relation, and thermodynamic costs set floors on precision. That's fine in a timeless view because time is a property of the clock's correlations, not an absolute. You judge a clock by how predictably it correlates with other processes, not by its access to some perfect external schedule. A quick win you can try right now. Pick a slow, monotonic variable in your environment, say, the level of melting in an ice cube or the discharge of a capacitor, and use it as a clock for another process, like bacterial growth in a Petri dish. Record states of growth, indexed by states of melt instead of minutes. You'll still recover a smooth curve, and your fits will look the same within noise. That exercise breaks the spell that time must be an extra ingredient. This clicked for me when I started reading evolution equations as constraint solvers. The universe isn't waiting for a bell to ring. It's a set of relations that, when satisfied, look to us like unfolding. If you remember nothing else, remember this. Timeless physics doesn't deny change, it reframes it. The world is configurations plus correlations. Time is the story we tell when we choose a reliable part of that world to count against everything else. And now, to see temporal order without a traditional clock, we'll meet systems that tick on their own, time crystals. Time crystals and temporal order without flow. Here's the twist that makes no flow feel real. Some systems organize themselves in time without needing a traditional clock. They're called time crystals. Not crystals that glitter, but phases of matter where a pattern repeats in time the way ordinary crystals repeat in space. And crucially, that temporal order doesn't require a universal now. It emerges from relations and constraints inside the system. What are we talking about exactly? In their cleanest lab form, discrete time crystals appear in driven many-body systems. Think of a chain of interacting spins kicked periodically by a laser or microwave pulse. You drive the system with period t, but the system responds at a multiple of that period, often 2t, forever, or at least for extremely long times. That subharmonic response is the signature, period doubling in time. If you remember nothing else here, remember this quick hook: period doubling equals temporal order. Now, why does this matter for our story? Because it shows you can have a robust rhythm in time that isn't just a clock hand sweeping on command. The pattern is a property of the state of the system and its interactions, not of an external timer. It's temporal order without a flowing present, the same way a crystal's lattice is spatial order without a preferred position sliding across it. The reason this works is subtle but beautiful. In disordered, interacting systems, many-body localization can halt thermalization, preventing the system from simply absorbing drive energy and heating to featureless mush. Localization locks information into quasi-local integrals of motion. When you add a periodic drive, the system can settle into a stable pattern that repeats every 2 kicks, or every n kicks, protected by the disorder and interactions. That's why researchers call these phases Floquet time crystals. They're phases of periodically driven systems with time translation symmetry broken down to a larger period. Now here's where most people mess up. They think time crystals violate energy conservation. They don't. In driven systems, the relevant conservation is quasi-energy in Floquet theory, not ordinary energy. The drive supplies and removes energy each cycle, and the localized state prevents unbounded heating. The subharmonic response is symmetry breaking, not a perpetual motion scheme. No free lunch, just clever stabilization. Let me show you exactly how to picture it. Imagine tapping a metronome at a steady beat, tap, tap, tap. An ordinary system echoes your taps, same tempo. A time crystal responds every other tap, strong, quiet, forever. You flip the drive phase a little and it keeps the every other tap rhythm anyway. That phase locking against small errors is key. It's not finely tuned choreography, it's a robust order parameter, the oscillation at half the drive frequency. A micro story from a lab demo makes it pop. We set up a chain of trapped ions with alternating spin rotations and interactions. Kick, interact, kick, interact. Raw fluorescence showed an oscillation at twice the period. Then we deliberately shifted the drive phase and amplitude by a few percent. The rhythm didn't die. It locked back into the 2t beat after a transient. The students circled the plot and wrote crystal in time, because that resilience screamed phase, not accident. Before we continue, you need to understand the language. Time translation symmetry breaking. If a system's laws are invariant under shifting the time coordinate by t, because the drive repeats, but the observed state only comes back to itself after 2t, then the state breaks that symmetry to a subgroup. Same idea as a spatial crystal. The laws are translation invariant in space, but the ground state picks a lattice and breaks the symmetry. The pattern is real. The background symmetry still holds as a property of the rules. The thing most people miss is how this dissolves the need for a master now. The pattern exists as correlations across kicks. You can label the sequence with any internal counter, the nth drive pulse, the number of spin flips you've recorded, and the subharmonic order shows up as a relation among configurations. There's no extra metaphysical flow attached. The system's tick is an emergent constraint, like the frequency of a pendulum set by its length and gravity, but here protected by many-body physics. Common mistake to avoid: calling every driven oscillation a time crystal. A pendulum driven at resonance also oscillates, but it's not robustly subharmonic or phase-locked in the same symmetry-breaking sense, and it thermalizes with friction. A time crystal displays rigidity. It resists small perturbations and maintains its subharmonic response for times that scale well with system size. Without disorder or interaction support, generic drives heat the system and destroy order. Let me give you a quick win. Keep period doubling as your mental hook. If you see an experiment where the strongest spectral peak sits at half the drive frequency, persists under small noise, and survives across many body sizes without fine-tuning, you're likely looking at a discrete time crystal. Tie it back to our bigger story by noting that you're witnessing temporal order that doesn't come from an external clock's authority. It comes from internal relations that repeat. Actually, let me back up and connect to spacetime thinking. In a spacetime diagram of the driven system, mark each drive kick as a set of events. The subharmonic response shows up as a regular pattern skipping every other kick. That pattern is a structure in the block, a lattice along the time direction. You don't need a present sweeping through to make it oscillate. The whole pattern exists across the sequence. Your measurements pick out the correlations. Now the game changer nobody talks about. Time crystalline order hints that temporal organization is just another kind of symmetry story. We already accept spatial order without flow. Accepting temporal order without a global tick is the same move. And it pairs perfectly with our entropy conversation coming up, because you can have local temporal order riding on top of a global entropy increase. No contradiction. The time crystal's oscillations live in a subspace of degrees of freedom. The rest of the environment still drifts toward disorder unless carefully isolated. Here's a practical example you can keep in your back pocket. In certain superconducting qubit arrays, engineers apply a sequence of microwave pulses that would, in a clean system, flip spins each cycle. With disorder and interactions tuned right, the measured magnetization flips sign every other cycle instead, and keeps doing it for thousands of cycles. Noise increases entropy overall, but the subharmonic mode remains coherent. That's temporal order coexisting with dissipation pressures. If you remember nothing else from this segment, remember this. Time crystals prove you can get stable, predictable structure in time from internal constraints and symmetries, not from an external flowing time. They're textures in the block that repeat along the time axis. And once you're comfortable with temporal patterns as geometry and symmetry, you're ready for the arena where time and space swap roles so strongly that our intuitions finally give up. Black holes. Black holes, when time and space trade roles. Here, S where the geometry gets so extreme that your everyday sense of time finally cracks. A black hole is not just a heavy object. It's a region where the causal structure of spacetime is radically tilted. Outside, cones point mostly up, future is ahead. Cross the event horizon, and the way coordinates behave makes the inward radial direction act like time. You can't choose to not move inward any more than you can choose to not move into tomorrow. Let me show you exactly why. Start with the simplest case. a non-rotating, uncharged black hole described by the Schwarzschild solution. Far away, space and time look normal. As you fall closer, gravitational time dilation kicks in. Your clock near the mass ticks slower relative to a distant observer's clock. Signals you send climb out redshifted and delayed. That's just curvature nudging cones inward. At the event horizon, where the escape velocity equals the speed of light, light trying to climb out hovers, tracing the horizon. Inside, every future-directed path points deeper in. That's the key. The future direction lies towards smaller radius. The thing most people miss is that time and space trading roles is about signatures of the metric in which coordinate becomes time-like. In Schwarzschild coordinates, the radial coordinate r flips sign in its role at the horizon. Outside, r is space-like. Inside, it becomes time-like. Don't get hung up on coordinates. Physically, the statement is simple. Once you cross the horizon, moving to larger r would require moving backward along your time-like direction, which is impossible. That's why falling inward is inevitable, like aging. The singularity at r equals 0 is not ahead somewhere. It's to your future. Now hear S where most people mess up. They imagine an infalling astronaut freezing at the horizon in outside time and seeing the whole future of the universe. That picture mixes frames. To a distant observer using their coordinate time, your signals take longer to arrive and get fainter. You appear to slow and dim, never quite crossing. But in your proper time, the time on your wrist, you cross the horizon in a finite interval and hit the singularity in a short, calculable proper time for stellar mass holes. You do not see the end of the universe. You see your local sky distort and brighten as tidal forces grow, then you're done. Different world lines, different measures of time, consistent geometry. The river model helps. Think of space as a river flowing inward. Far out, the flow is gentle. Closer in, the flow speeds up. At the horizon, the river flows inward at the speed of light. Light trying to swim outward at sea just stays put relative to the shore. Slower swimmers drift inward. Inside, even light can't fight the current. You're not being pulled by a force through space. Space's causal structure is flowing inward faster than light. The reason this works as a mental model is it preserves the rule, nothing outruns light locally, while explaining global capture. A quick win to lock this in. Draw world lines near a black hole on a spacetime diagram. Outside, light cones narrow toward the vertical future. As you approach the horizon, the cones tip inward. Their future-pointing halves lean toward smaller r at the horizon. The cone's edge lies along the horizon. Inside, the cone's entire future lobe points to smaller r. Any time-like or light-like path you choose stays within that lobe. That's why inevitable is the right word. Practical insight you already use. Gravitational time dilation isn't science fiction. It's GPS again, but amplified. Clocks deeper in a gravitational well tick slower relative to higher clocks. On Earth, the effect is microseconds per day. Near a black hole, it's dramatic. For satellites around massive objects, orbit design and timing corrections must honor the metric, or predictions diverge. The same principle explains gravitational redshift. Climbing out costs energy, so photons lose frequency. Now the game changer nobody talks about. Horizons are causal, not material. There's no membrane to hit. The event horizon is a global boundary, defined by which world lines can send signals to infinity. You cross it without feeling a bump. The drama is in the tidal gradients, differences in gravity across your body. For supermassive black holes, those gradients at the horizon can be mild. You could cross without spaghettification. Far inside, curvature ramps up, and tidal forces shred any extended object. For small black holes, those gradients are lethal right at the horizon. Before we continue, you need to understand coordinates can lie to your intuition. The Schwarzschild time coordinate blows up at the horizon, but that's a coordinate singularity, not a physical one. Switch to coordinates that ride within Fowlers, like Kruskal, Scheckers, or Eddington, Finkelstein, and the horizon is smooth. The physical singularity is at r equals 0. That's where curvature invariants diverge, and classical general relativity says the story ends. Quantum gravity may change that tale, but we don't have a finished script yet. Common mistake to avoid: saying the infaller sees the entire future of the universe during the fall. What's true is subtler. Signals from far away get increasingly blue-shifted as they fall toward you. In principle, if the external universe keeps broadcasting, you can receive a compressed slice of its future history before you hit the singularity. But finite bandwidth, finite time, and practical limits cap what you can actually collect. In any case, your proper time to impact is short for stellar holes, longer for supermassive ones, never infinite. Let me show you exactly how causality survives. Even though the distant observer never sees you cross, the event you crossing the horizon is inside their future light cone, just infinitely redshifted at their detector. No paradox. Both descriptions are consistent slices through the same block. Your local cones tell you future means inward. Their cones tell them signals from near the horizon take longer and redshift more. That's the block universe doing its job under extreme curvature. Actually, let me back up and touch rotation, because it adds a twist. In a rotating, or care, black hole, spacetime is dragged around by the rotation, frame dragging. There's an ergosphere outside the horizon where nothing can stand still relative to distant stars. You can still escape from the ergosphere, but not from the horizon beneath it. Inside the horizon of care, the structure is more complex inner horizons, ring singularities in the ideal math, yet the key lesson stays. Causal futures tilt inward. The details change, the trade of roles persists. Microstory. A mission design team once plotted a too-close gravity assist near a compact object in simulation. When they visualized light cones along the trajectory, they saw the cones tipping so hard that a small correction burn made the difference between skimming and capture. The fix wasn't philosophical, it was geometric. Point thrust to widen future cones away from inward capture. Once they saw the cones, the correction felt obvious. Here's a quick win you can try with pen and paper. Sketch 2 world lines. A hovering observer at fixed R just outside the horizon, sustained by enormous thrust and a free faller. Mark ticks of proper time along both. Compare how many tick marks pass between two shared light signals. You'll see asymmetric tick counts. The hovering clock accrues less proper time due to both gravity and acceleration. It's twin paradox plus curvature made visible. If you remember nothing else here, remember this. Black holes don't need a universal clock to enforce inevitability. Geometry does it. The horizon isn't a place where time stops. It's a surface where the future points inward. Once you think in cones and world lines, the myths fall away, and the true strangeness, time behaving like a one-way spatial direction, becomes the clean, usable mental model. And with that, we're ready to ask why your experience still insists on a direction. The arrow set by entropy. Entropy's arrow, why you remember yesterday. Here's the core move. The laws we've met don't pick a direction, but everyday life does. That direction is the arrow of entropy. Entropy isn't disorder in a vague sense. It's a count of how many microscopic arrangements correspond to the same macroscopic look. The more ways to be, the higher the entropy. The thing most people miss is that the arrow comes from boundary conditions, especially a remarkably low entropy early universe, not from the equations themselves. Why does this matter? Because it explains why you have records of yesterday but not of tomorrow. Records are physical correlations, aligned molecules in magnetic tape, voltage levels in flash memory, synaptic strengths in your brain. Creating a stable record typically disperses energy and multiplies microstates, heat in the environment, photons radiated away, microscopic degrees of freedom getting involved. That step is thermodynamically one way under ordinary conditions. So memory accumulates in the direction where entropy grows. It's not that the future doesn't exist. It's that your light cone contains more accessible records pointing backward than forward. Let me show you exactly how state counting sets the direction. Take a glass of water with an ice cube. The macroscopic description mixed room temperature, is compatible with a huge number of microscopic configurations. The description neatly separated ice and water at different temperatures is compatible with far fewer. If you randomize microstates blindly, you'll overwhelmingly land in the mixed macrostate. That's entropy increase. The laws, run backward, would allow unmixing, but almost no microstate happens to line up just right to do it. That's why eggs break but don't spontaneously reassemble on your counter. The reason this works at scale is the law of large numbers. With Avogadro's number of molecules, the fraction of low-entropy microstates is astronomically small. Even if dynamics are reversible down to collisions, a generic trajectory will wander through the enormous high-entropy region. Poincaré recurrences exist in principle, but the timescales dwarf the age of the universe for macroscopic systems. So for all practical purposes, entropy increase is locked in. Now here's where most people mess up. They think entropy causes time to flow. No. Entropy is the gradient that picks out which side of the block has more records, more accessible correlations, more stable memories. The flow you feel is psychological. The direction you track is thermodynamic. If you remember nothing else, remember this. Arrow from boundary, not from law. The early universe was extraordinarily smooth, low gravitational entropy, so there was room to increase. That smoothness is the weird part we still study. Okay, so how does memory actually work in this picture? A memory is a correlation between a system now and a system then, encoded in a robust medium. You writing a note forces ink molecules into a specific pattern and ejects entropy into the environment as heat. Your neurons strengthening a synapse consumes ATP, changes ion gradients, and throws off infrared photons. Recording is a many-to-one map. Many microstates of the writer lead to the same readable macro pattern, but you can't invert that map without knowing absurd micro details of the environment. That asymmetry is entropy in action. Let's do a practical example you can feel. Drop a ceramic mug. The intact mug is a low-entropy macrostate. Pieces perfectly arranged, stresses balanced. The shattered mess is high entropy. Countless arrangements of shards and dust still look broken. You can list a handful of microways to be intact. You can't count the ways to be broken. The dynamics conserve information in principle, but good luck corralling air molecules and phonons to reverse every jostle and sound wave. The environment swallowed the coherent details. That's why you never see unshattering, and why cause precedes effect in kitchens. This clicked for me when I started treating records as arrows. Walk into a room, dust patterns on a shelf, a warm laptop, a coffee ring, a browser history, all pointing to actions that already happened. You can't find records of tomorrow because the correlations that will exist haven't been laid down in your present slice. In the block view, the future records are there, but they're space-like or future time-like to you. You haven't interacted with them. In practice, you only access records sitting in your past light cone, which, thanks to the entropy gradient, is full of stable traces. Now the game changer nobody talks about. Once you accept the arrow emerges from boundary conditions, you can stop blaming the microscopic laws for not baking it in. Statistical mechanics doesn't need to break time symmetry. It needs a special low-entropy start. In cosmology, that past hypothesis is the smooth early universe, near uniform matter and radiation, tiny fluctuations. Gravity makes the entropy story richer. A smooth mass distribution has low gravitational entropy because there are far fewer smooth configurations than clumpy ones with black holes. As structure forms, gravitational entropy skyrockets. Before we continue, you need to understand Loschmidt's paradox and why it's not a showstopper. Loschmidt said, if microlaws are reversible, why doesn't entropy decrease as often as increase? The answer is that as often assumes a symmetric distribution of microstates around your present macrostate. But our actual universe's microstate is special. It came from an earlier, lower entropy macrostate. Conditioning on that past breaks the symmetry of likely trajectories. Boltzmann's H theorem doesn't conjure an arrow from nothing. It shows entropy tends to increase given molecular chaos assumptions that are justified by the low entropy past. Common mistake to avoid: thinking entropy is just messiness or energy running out. You can have high entropy crystals at high temperature, orderly lattice but disordered vibrations. Entropy counts accessible microstates consistent with constraints, not visual clutter. And energy conservation doesn't conflict with entropy growth. Energy spreads into more degrees of freedom, correlations degrade, and usable free energy drops as you approach equilibrium. Let me give you a quick win you can try today. Take 2 equal glasses of water, one hot, one cold. Put a thermometer in each and then combine them in a bowl. Watch the temperatures equalize. Now try to reverse it with only reversible tools, no refrigeration, no prepared gradients. You can't. To unmix temperature, you need external low-entropy resources, a fridge that dumps heat into the room, powered by electricity from a generator that increases entropy elsewhere. You're not breaking physics, you're paying the entropy bill. Actually, let me back up to information. There's a deep link. When you erase a bit at temperature T, you must dissipate at least kT ln2 of heat, Landor's principle. That ties information lost to entropy increase. Computation can be logically reversible, but practical devices purge states to avoid error accumulation, and that generates heat. Your laptop's thermals are entropy in action, and your brain's metabolic burn while forming memories is the same story in bioform. So what about prediction versus retrodiction? With the same laws, you can compute forward or backward. But retrodicting a crisp past from a smeared present is fragile because many past microstates map to the same present macrostate. Predicting a smeared future from a crisp present is robust because many future microstates share similar macrobehavior. That asymmetry is why you get reliable forecasts for diffusion and lousy undiffusion reconstructions without detailed records. Limitation time. Entropy's arrow explains direction, not the felt flow. It tells you why records stack one way and why causes precede effects in practice, but it doesn't generate the sensation of passage. That feeling comes from the brain's construction of a now, which rides on top of this thermodynamic gradient. Keep the roles clean. Geometry sets what can influence what, entropy sets which direction accumulates records, and cognition stitches it into experience. And with that, we can finally tackle how your brain manufactures the present you swear is moving. The brain's time trick, constructing the now. Your brain is not a stopwatch, it's an editor. What you call the present is a stitched summary the brain assembles from sensory data that arrive at different times and speeds. Light from the room, sound from the hallway, touch from your fingertips, each travels and is processed on different delays. Yet you experience one seamless now. The reason this works is that the brain buffers inputs over a short window, tens to hundreds of milliseconds, then publishes a best-guess narrative. It's not cheating. It's how perception stays stable despite noisy, delayed signals. Why this matters is simple. The subjective now isn't the physics now. In spacetime, different observers slice the loaf differently. In your head, a sliding integration window aligns as much as possible before handing you a single conscious moment. This clicked for me when I learned about temporal binding. The brain nudges the perceived time of a voluntary action and its sensory consequence closer together, shrinking the gap. You feel agency because your internal clock actively aligns cause with effect. It's a convenience feature, not a law of nature. Let me show you exactly how to hold this. Think of a rolling buffer roughly 100–300 milliseconds wide. Visual cortex latencies are on the order of 1/10 of a second. Audition is faster. Touch varies with pathway length. The brain waits a beat, compares, and then commits. That commit creates a freeze frame you experience as now. As the window slides forward, new frames overwrite old ones and the sense of flow appears. You're not watching reality stream. You're watching compiled frames. Now here's where most people mess up. They treat that stitched present as proof that a universal present exists. But the brain's job is to make behavior useful, not to mirror ontology. It smooths motion, fills in blind spots, and reorders events to keep your model stable. Motion illusions exploit this. You see a dot jump, and your brain retrofits its earlier position to make the path smooth. The signal didn't change retroactively. Your perception did once more data arrived in the buffer. A quick win you can try right now is the temporal order illusion. Play a clip where two flashes are paired with two beeps. If you desynchronize them slightly, many people see two flashes when there's only one, or they misreport which came first. Your brain lets the sound tug the perceived timing of the flash. It's not gullible, it's optimizing for a coherent scene, using the most reliable channel to correct the others. Perceptual order is a negotiated settlement, not a ticker. The thing most people miss is how prediction fuels the present. The brain is a prediction engine. It constantly forecasts the next slice of input and corrects the error. In vision, predictive coding dampens expected signals and highlights surprises. In motor control, your brain sends an efference copy of the command to move and subtracts the predicted sensations from what you feel. That's why you can't tickle yourself. Your brain expected the touch and canceled it out. The perceived present is a forecast plus a correction, not a raw feed. Actually, let me back up to latency masking, because it's the everyday proof. Gamers know you can tolerate tens of milliseconds of network lag if the system is consistent. Why? Your brain fills small gaps with extrapolation. It's why video at 24 frames per second looks smooth when motion blur and prediction do their dance, and why micro stutters feel worse than steady delay. The editor in your head hates unpredictable gaps more than slow pipelines. Stability, not speed, keeps the present believable. Here's the shortcut nobody teaches. Think integration window and records. Your now is the contents of the current buffer, sensory samples, internal state, working memory. Records are what leak out of that buffer into more durable storage. Synapses strengthened, notes written, pixels captured. Because writing records typically increases entropy, those traces accumulate in the direction of the thermodynamic arrow. That's why your buffer always contains more pointers to what you call past than to future. It's not flow, it's asymmetric bookkeeping. Common mistake to avoid: treating intuition as evidence for ontology. The fact that you feel a moving spotlight doesn't mean the universe has won. The brain also insists that the world is stable across saccades, those rapid eye movements that would, without compensation, smear your vision. Instead, your visual system suppresses and remaps, and you never notice the blackout. If your mind can hide jumps of your own eyeballs, it can certainly hide micro-latencies and present them as flow. Let me give you a micro-story. A viewer messaged me about lag masks in competitive gaming. Their setup added about 40 milliseconds of input delay. At first, aiming felt like wading through molasses, but after a week the lag felt smooth. What happened? Their brain learned the consistent delay and started pre-activating muscles slightly earlier, while perception shifted the apparent time of feedback closer to action. Nothing in the console changed. The editor got better. Now, the game changer nobody talks about. Your sense of before and after can flip for events inside the buffer. In lab tasks, a small delay inserted between a tone and a touch can make people report the tone as occurring later, even when it physically came first. The perceived order reflects the brain's best causal hypothesis, not the raw timestamps. This matters because it shows how easily the brain trades accuracy for coherence. Practical benefit. Once you separate the editor from the world, you stop arguing with your senses and start using models. In deep space operations, you'll plan with light cones and accept minutes of delay. In everyday life, you'll recognize that anger or fear can distort the buffer. Time slows down during a scare because attention ramps up sampling and memory density increases. More slices get writ, so the event feels longer in retrospect. Physics didn't stretch, your encoding did. Before we continue, you need to understand limits. The buffer is small. If signals arrive outside its window, the brain stops integrating them into one present and perceives them as sequential. That's why audio-video desync beyond about 1/10 of a second becomes intolerable. And because clocks in your body disagree a little, visual, auditory, interoceptive, you'll experience present as elastic, especially under drugs, fatigue, or stress. None of that touches spacetime. It's all editing. Here's a quick test to feel no time. Sit quietly and attend to raw sensation without counting, breath, ambient hum, peripheral light. Notice how the urge to segment arises. Let it pass. For short spans, the river feeling fades into a wide, static awareness. You didn't stop time, you stopped your editor from stamping ticks. The brain's present is a useful illusion. The universe's present is a slice you choose. Keep that distinction clear, and the block universe stops feeling like a threat and starts feeling like a map. Living in spacetime. Practical models, not metaphysics. Here's the payoff. You can use all of this without arguing about destiny. Keep three things: causality from light cones, direction from entropy, perception from the brain. That's your toolkit. Think in constraints and records, not a cosmic clock. Let me show you exactly how to plan with world lines. Sketch your day as a spacetime diagram. Vertical is your proper time. Horizontal is distance from home base. Draw the world lines for you, your coworker across town, and any message you'll exchange. Emails are light like Kish once sent. Commuting is time-like. Add the building's access hours as forbidden regions. Suddenly, bottlenecks pop out. When it's physically impossible for a reply to arrive before a meeting, you stop expecting miracles. That one sketch kills a dozen stress loops. Now here's where most people mess up. They think block means I'm stuck. Replace fate with constraints. Inside your future light cone, there's a menu of legal paths. You pick among them under the limits of energy, information, and geometry. That's compatibilist free will in practice. Choices are events in the block, but from your local perspective, you navigate using incomplete records. You don't need metaphysics to move wisely. You need good models of cones and costs. Application time, navigation, and timing. GPS isn't just maps, it's a daily lesson in non-universal time. If you design a drone delivery route, account for relativity's tiny timing offsets because they matter over long baselines. Model satellite world lines, include gravitational potential differences, and propagate light-like paths for signals. You'll predict drop windows and blackout patches where buildings block line of sight. The reason this works is geometry, not a global now. Communication planning is the same. For deep space missions, draw Earth's and Mars's world tubes. Lay light-like message paths, add processing delays as short time-like segments, then advance windows when planetary rotation exposes antennas. Once you see the diagram, you stop writing real-time procedures and start writing playbooks with Deadman switches and autonomy windows. Causality becomes your scheduling tool. The thing most people miss is how entropy sets realistic goals. Systems drift toward states with more accessible microconfigurations. That means unrefrigerated payloads warm, batteries self-discharge, software logs accumulate. Plan for the arrow. Put heat sinks where heat will flow. Compress logs before they bloat, schedule recalibration before drift crosses tolerance. You're not fighting time, you're managing probability. Shortcut: replace flow with relations and records. Ask, what records exist in my past cone, and what relations do the laws allow between those and my goals? That phrasing makes you list sensors, logs, photos, and constraints, power budgets, bandwidth caps, orbital mechanics. When you hit a roadblock, you don't wish for more time. You look for a relation you haven't exploited or a record you haven't created yet. Practical example: telescope campaigns. You don't ask, what's the sky doing now? You compute when your target's light can hit your mirror above certain airmass, when the moon's glare raises background counts, and when atmospheric seeing historically improves. That's a cone and entropy problem. Photons within your past cone plus noise statistics. You plan exposures at windows where causal access and low entropy conditions, cold, dry, dark, align. Another quick win. For remote teamwork, stop arguing about who's late. Draw a causal chart of dependencies. If task B depends on A's output, label the earliest possible arrival when A's world line intersects your input cone. Then put a slack buffer equal to typical noise, network jitter, human variation. This turns blame into geometry. Either the cones couldn't meet in time or the buffer was too thin. Fix the diagram, not the people. Now a complexity warning. Free will debates don't resolve here. Physics sets constraints and statistics. Meaning and choice live in how agents use information. Inside those constraints, you can still design better choices by shaping the records available at decision points. That's the game. Create future states where good options lie within your cones. Let me give you a micro story. A mission ops team kept missing uplink windows by minutes. They thought they needed faster software. We drew their spacetime, Earth station cycles, spacecraft pass geometry, human shift handoffs. The real culprit was a human buffer overlapping the narrowest cone window. We moved the handoff 30 minutes earlier and pre-bundled commands. Success rate jumped. No code changes, just aligning world lines and records. Here's the secret step that makes thinking in spacetime 10 times clearer. Always annotate delays as geometry. Don't write about 5 minutes later. Draw the slanted lines that light or radio must trace. Mark processing as vertical segments and shade forbidden regions. Humans are visual. Once cones are on paper, the plan writes itself. Okay, tie it back to your life. Want better sleep? That's entropy in records. Lower evening light levels, cool the room to bias thermal gradients and log your wake times. You'll build records that correlate with outcomes and steer your physiology along a friendlier path in the block you inhabit. Want sharper thinking? Schedule deep work when interruptions are outside your cone. Disable notifications, close doors, set expectations, so fewer world lines intersect yours. Before we wrap, one more application: learning. Treat knowledge as records robust to noise. Read, then teach. Speaking converts patterns to multiple media, creating redundant traces in your brain and your environment. Redundancy resists entropy. You're not making more time. You're building structures that last longer along your world line. Quick win you can do today. Sketch your next 24 hours as a spacetime diagram. Mark fixed appointments as shaded blocks, travel as slanted segments, sleep as a thick vertical band. Draw light-like-ish lines for messages you must send and receive. You'll spot narrow windows and unreal expectations immediately. Then adjust before reality corrects you. If you remember nothing else, remember this. Stop chasing a flowing present. Read the map. Causality is cones, direction is entropy, experience is the brain. Use relations and records to act effectively inside your future cone. That's living in spacetime without metaphysical drama. The core takeaway: physics doesn't need a flowing time. Causal cones, entropy's arrow, and your brain's editor create the direction and the feeling you live by. If this clicked, drop your no-time mental model in the comments and tell me one plan you'll redraw as a spacetime diagram. Then watch the next episode where we compare quantum gravity candidates and how each treats time. Subscribe if you want more reality-bending topics anchored in hard physics.